So we have proved the connection lemma, and now we want to prove observing lemma. So for let's try this way. So the beta is more than 1/100, and then n is sufficiently large. And if G is an n-vertex graph with minimum degree at least 2/3 plus beta n, then you can find the curve path PA in G with, say, at most beta to the 10n vertices, such that it is an observer. So for every subset U, which is outside of this path, which has size at most beta to the 20n, there exists a square path. Square of the path, the PAU in G, such that its vertex set is exactly the vertex set of the PA, and the union with V. Moreover, this PAU has the same end pairs as PA, meaning that the PA starts with the vertices A, B, and C, E, and PAU also starts from A, B, and then ends with C, D, and so on. So these are called the end pair. Okay, and in order to prove this, we will proceed similarly with the Dirac theorem proof, the approximate Dirac theorem proof that I explained in the previous video. So first, we analyze how we can observe one vertex. Let's say you have a vertex B, then let's say you have 5 vertices A, B, C, D, E. Now let's say A, B, X, C, D. Then, if you have these parts, and then if this is adjacent to all of them, then A, B, C, A, B, X, C, D itself is the square path, as well as A, B, X, B, C, D is also a square path. So, if can observe this, so we say that the tuple, 5 tuple X, A, B, C, D, or vertices observes B if all 5 vertices are in the neighborhood of B, and A, B, C, D are all neighbors of X, and A, B, C, D is a path. So, exactly if we have this. And minimum degree condition give us that for each B, there are many. There are, say, 2 times beta 5 and to the 5 tuples that absorbs this specific vortex B. Why? You know that in its B, you have neighbors. How many neighbors? It's many neighbors, and you choose X. So choosing X takes this many ways, and you consider the vertex set, the common neighborhood of this B and X. It has size what? At least like 1/3 plus 2 beta n. So, and there, what? You know that, let's say this is U, and the minimum degree of this is at least 3 beta n, because what? For each vertex here, you know that all three of them, the common neighborhood of all three of them is at least 3 beta n. So you have this. So this vertex has at least 3 beta n neighbors here. So we choose A in here in, say, this many ways. And we choose, say, B in the neighborhood of A, and C as the neighbor of B, and D as the neighbor of C. And each time, like 3 beta n way, 3 beta n way, 3 beta n way. So, how many? Choosing X, there are this many way, and then choosing A takes this many way, so U is at least like, and choosing B, and choosing C, choosing D, so in total it's like, how many? It's at least 2 times beta to the 5 and 5 way. So there are many tuples. So 5 tuples, so n to the 5 many, some quantitative n to the 5 many choices. So this proves the claim. Let, like, Hardy A, the B is the family of 5 tuples that observes this B. Then we have that it has at least 2 times beta to the 5 and to the 5. So we now have this, and then using that, we will construct the observer. So let's consider its claim. So how do we do it? So for each vertex, we have many choices that observe it, many 5 tuples. And what we want is we want the path that observe any set of the vertices. So for each vertex, there are many choices. So what we do is we randomly choose many 5 tuples so that we can ensure that every vertex here is observed by many 5 tuples. So we can show this. So there exists, you can find the family f of and most, say, 2 times beta to the 14th and is joint, say, 5 tuples of vertices of G, such that for every vertex B, we have that in this family F, at least beta to the 20 and many 5 tuples are observing the specific vertex B. So, proof as I mentioned, we select family, the F, call the F prime or 5 tuple or vertices at random by what? Including each of the n times n minus 1 times n minus 2 times n minus 3 times n minus 5 many tuples independently with probability, equal probability, which is a beta to the 14 times n to the negative 1. So any 5 tuples of distinct vertices, you randomly choose. Then by Chernow bound, you can show that the number of 5 tuples chosen is almost 2 times beta to the 14 times n. So, I mean, if you just multiply these two, then that's the expectation. It is like almost twice of this. So it's almost twice of this. And we know that for each p, we have that this is a lift beta to the 19th n. Why? So this has like here, this has size a listed. Then probability of choosing is this, so 2 beta 5 n to the 5 with the probability, no, sorry, so this is 4. So we want to choose linearly many. So this is 4. And then the probability that each one is included is this, so this is the expectation. And using channel bound, we show that this is at least, I mean, half of the expectation. And this happens, right, with probability at least 0.99. To be more precise, you can actually write 1 minus e to the some exponent, but I mean, it's enough to just have this probability. Furthermore, so we randomly chose it, but we want to make sure that they are disjoint. So in order to get the disjoint one, we compute the expected number of intersecting pairs of 5 tuples in this curly F prime is what? At most, there are n to the 5, at most n to the 5, sorry, 5 many tuples, and you choose one of them. In each tuple, you have a x, a, b, c, d, and you choose one of them. And for this one, there are like, I mean, again, you choose the 5 other, and then this one vertex can play the role of either x or a or b or c or d. So there are also 5 ways. And then choosing this is playing the role of x or a or b or c or d in new 5 tuple. And then you can choose the remaining 4 vertices in n to the 4 way. And this is the possible number of tuple. And then once you have that, the probability that both of them are chosen is this. So this is like this small number. And by Markov's inequality, the probability that this number is twice of its expectation is at most half. So with probability at least half, we know that another property that there are at most 50 beta to the 28 and pairs of intersecting 5 tuples in this cardiac prime. Then with probability at least like 0.099 plus half minus 1, which is positive number, a random family F prime satisfies these three properties, F1, F2, F3. And once you choose such a choice, we delete the or 5 tuple that it affects other 5 tuple. And also all 5 tuple if that does not observe any vertices. And let curly F be the resulting collection. Then what? So each one is, so for F prime, this one intersection is at least beta to the 19 and then, but how many we have deleted is smaller. So we know that. So that shows that this property holds. And also, I mean, the number here is at most 10 number is also easy to check. So we have this and then we have deleted a few more. So this proves the claim. So now we consider this F, which is like F1 to FF as in the claim. And what? Each of Fi has like A, B, X, C, D. You have this. And what you do is that let's say you take I plus 1, then you take this and then this. And like you consider the graph G and you delete the vertices in all of them. And so what you do is that, let's say, like U prime be a subset of the vertices with the most beta n over 2. Then what? you delete this U and all the vertices where. And then you take, say, this one is CD and this one is AB. You put ABCD. You delete all the vertices here, but you don't delete the ABCD. Then this graph has minimum degree at least 5 plus the beta over 3n. Because how many we have deleted? It's much smaller than beta n. And this one is also smaller. So we have deleted less than 2 beta over 3n vertices. So this has large minimum degree. So by connection lemma, we find like the vertices Ci such that is Fi Ci Fi plus 1 from the square of the path. And this is almost like 100. 4 times k cube, and k is like 3 here. So maybe 200 to be safe. And what? And then we add this Ci to U and repeat. So you take F1 and F2 and then you connect it by using connection lemma. And then F3 you also connect, F4 you connect, and then every time you connect, you take the new vertices introduced here as U prime, and then you make sure that the new one is disjoint so that you actually get the square path. And then after doing this gives a desired PA with length and most what? 200 times F is like 200 times 2 times beta to the 14 times N, which is like more than beta to the 10 times N. And this proves the observing lemma because what? Now, exactly we have a square path with almost this many vertices. And then in that square path, you have lots of 5 tuples that absorbs specific vertex. So whenever you have a small, like beta to the 20 and vertices, and each one of them you can choose like in this PA, for each one you can choose the 5 tuple that absorb it. And for this one, you can choose another 5 tuple that absorb it, and so on. Because each one of them, you have at least like beta to the 19 and choices. I mean, beta to the 20 and choices, or 5 tuple that observes it, which are all disjoint. So that at every time you can forget about the 5 tuple that's already been used, you can already choose the new one that observes it. So altogether, it's, observing this arbitrary set U. And that's the observing lemma. And the following, say, legible lemma is easy. That again, you have this, and then G is an n-vertex graph with a minimum degree at least, 2/3 plus beta times n. Then there is a subset R as a reservoir. With its size being like very close to beta to the 20 n over 2, say, such that every v satisfies that its neighbor, the number of neighbors in here in R is bigger than 2 over 3 plus beta over 2 times R. So this is easy. You just apply the Cherenkov bound. You just take a random subset as each vertex is included with the probability beta over 20 over 2. And with Cherenkov bound, you can show that the number of vertices chosen is concentrated around this expectation. So it's here with a probability 0.99. And for each vertex, you compute the probability that it holds. And that's again 1 minus e to the expression here using Cherenkov bound. And you take the union bound to ensure that for every vertex B, then you can prove this reservoir lemma. So I'm not going to write down the proof, but this one is kind of a standard application of Cherenkov bound. Now we are equipped with all the lemmas that we need to prove this approximate Portas conjecture. And maybe we will do that in the next video.